On this video, we're going to be practicing interpreting infrared spectra. I'm going to stop the video several times and ask you to do the problems, and I would really encourage you to stop the video and have a go at the problems before I solve them. To do this exercise, you're going to need access to an infrared table, a table with infrared absorption for various functional groups. You have an option on the module blackboard of a table you can use, or you can find any table you want. So this is the first problem. You are giving a molecule, an unknown compound that has this formula, C5H10O, and you are giving 5 different options of what that compound might be. And here you've got the infrared spectrum. So to what of these compounds this spectrum corresponds? A, B, C, and D. Before you start the problem, think about it. Try to identify the key functional groups for each of these options and see if you find those bands in the infrared spectrum. So stop the video now, please. So hopefully you have stopped the video and have a go at the exercise. How would I approach it? Well, if I look at the structure of the compounds I've been given, I can identify that A and C have a carbonyl group, a carbon double bond oxygen. So I would expect a very strong band associated with that carbonyl group, which would appear around between 1600 and 1800 inverse centimeters in the infrared spectrum. So somewhere around here, and very strong, occupying almost the whole of the y-axis. And I have nothing, I mean, I do have a band here, but it's definitely not as strong as I would expect for a carbonyl group. So straight away, I can discard compound A and compound C as my unknown, because I'm missing that carbonyl group. And that's very important. In infrared spectrum, it's as important the bands that appear to interpret the bands that appear as the bands that do not appear, and therefore indicate that that functional group is not present. If I look at the spectrum, I can observe a very broad band, a strong and broad band, around 3400. That shape, that broadness, is typical of an alcohol, a hydroxyl group. And that allows me to eliminate straight away compound B, because that's an ether, it's not a hydroxyl group. So my only options now are D and E. And at the moment, I don't think I would be able to identify D and E with respect to that infrared spectrum, because they are all carbon-carbon single bonds. Yes, one is a cyclic compound, the other one is a linear compound. But one thing that I've been given is the structural the formula of the compound. I can count the carbons, hydrogens, and oxygens that my structures D and E have and work out which is the right compound. So they both have 5 carbon atoms. That's not helpful. They both have 1 oxygen. And if I count the number of hydrogens, this one has 2, 4, 6, 8, 9, and 10. And this one has 3 on these 2 carbons, so 6, 7 in the carbon here, 9 counting the 2 hydrogens that are going to be here, 11 with the 2 hydrogens that are going to be here, and 12 if I count this hydrogen. So I would expect, well, that structure does not correspond to the formula C5H10O. It has too many hydrogens. So the correct compound that this spectrum corresponds to is compound E. Again, another practice problem. And again, I'm going to ask you to stop the video, have a look at the different options you've been given, and identify to which this particular spectrum we have here, to which compound it corresponds. As again, in the previous example, look at the bands that are present and the ones that are absent, and it will give you an indication of which compound you're looking for. Stop the video now, please. So how would I approach this problem? Well, the first thing I can observe here is this very strong band here at 1700 inverse centimeters. Very sharp, very strong, the right position to be a carbonyl group. So this spectrum corresponds to a compound that has a carbonyl group. That allows me to reject straight away compound A, that is an alcohol, compound B, which is an ether, and compound E, which is another alcohol. And then I've got the compounds, the only possible options are compound C and D. And I might be able to maybe look at, this is a carbonyl group which is part of an ester, and this is a carbonyl group that is part of a ketone. So there are some difference in position that can be observed between a carbonyl group that belongs to an ester or a ketone, and I might be able to look into those if needed. But it's an easier way of identifying which compound it is. And it's again by using the formula we have been given. That compound has only one oxygen. Therefore, that eliminates compound C straight away since it has two oxygens. So all those 5 possibilities, the compound to which this spectrum corresponds is compound D. Again, another problem. You have the formula, you have the 5 different options, and you have the spectrum. To what compound this spectrum corresponds? A, B, C, D, or E? Stop the video now, please. So let's inspect the spectrum. The first thing I notice is that this spectrum does not correspond to a compound that has a hydroxyl group because there's no broad band in the region of the spectrum. That allows me to eliminate straight away options A and B because they are both alcohols. Another thing to notice is in the region of the 16 to 1800, somewhere around here, there's no strong band, which would be characteristic of a carbonyl group. So that spectrum does not correspond to a compound that has a carbonyl group, and that allows me to eliminate D straight away. My only options left are C and E, and they are both ethers. One is an epoxide, E is an epoxide, C is a linear ether, and again, I might be able to identify some differences between them, but the easiest thing now is, because we have been given the formula of the compound, is to look at the number of carbons, oxygens, and hydrogens we have in those 2 structures. And in the case of this compound, the only option that has 6 carbons, 14 hydrogens, and 1 oxygen is option C. So that is the compound to which this spectrum corresponds. Problem 4. Again, you have 5 options. You have one infrared spectrum. To which of these 5 compounds is more likely to correspond the infrared that you have been given? Stop the video now, please. So if we look at the infrared spectrum, 2 things immediately spring to mind. One is the presence of a very strong band around 1700 inverse centimeters, which is typically indicative, or it is indicative of a carbonyl group. And of all the options have been given, that allows me to eliminate straight away option E, because it has an ether group and a hydroxyl group, but not carbonyl bond. That still gives me with 4 options. The next thing I look at is the area around 3000, 3500, this area here, and I have a broad band. And if you see, it's a broad band, which is indicative of a hydroxyl group. So I probably have a hydroxyl group. Well, I probably have a hydroxyl group. It's a very broad band. I notice also that it's broad but not defined as in previous problems. It overlaps the carbon-hydrogen stretching bands. So that's interesting, and it kind of indicates that I probably have a carboxylic acid. The fact that I have a hydroxyl band allows me to immediately discard A and C, because none of them are going to have, they don't have a hydroxyl group. Then they're going to have a hydroxyl stretch band. So my only options are B, which is a carboxylic acid, butanoic acid, and D, which is a hydroxyl and combined with a ketone. So it's a compound that has a hydroxyl group and a carbonyl group. From those two options, the most likely one is going to be B, because this shape of hydroxyl band, broad and overlapping the carbon-hydrogen stretch bands, is quite characteristic of carboxylic acid, and is due to the strong hydrogen bond that is formed between the different molecules of acid interacting with each other.